Software development is more than just writing code. It's about transforming ideas into reality through technology. It's a creative process that demands a blend of technical expertise, problem-solving skills, and a deep understanding of user needs. Like any craft, mastering software development requires adherence to fundamental principles and best practices. This essay will explore the essential principles and methodologies that underpin successful software development. We will delve into the software development lifecycle, a structured approach that guides projects from conception to deployment and beyond. Along the way, we will examine various development methodologies, each with its own strengths and weaknesses. Finally, we'll touch upon common challenges faced by software developers and emphasize the importance of continuous learning in this ever-evolving field. At the heart of software development lie a set of core principles that serve as guiding lights for building robust, maintainable, and scalable software. These principles, often interconnected, provide a framework for making informed decisions throughout the development process. Abstraction, a cornerstone of software engineering, allows developers to manage complexity by hiding unnecessary details and presenting only the essential information. Imagine trying to understand a complex machine by looking at every single nut and bolt. Abstraction lets us see the bigger picture, focusing on the machine's functionality rather than its intricate inner workings. Modularity, another essential principle, encourages breaking down complex systems into smaller, more manageable components or modules. Each module encapsulates a specific functionality, making the system easier to understand, develop, and maintain. Think of a house built room by room. Each room serves a distinct purpose, and modifications to one room don't necessarily impact others. Encapsulation, closely related to modularity, emphasizes hiding the internal workings of a module and exposing only a well-defined interface for interaction. This principle promotes information hiding, protecting the module's internal data and logic from unintended external access. It ensures that changes within a module don't ripple through the entire system, enhancing stability and maintainability. The software development lifecycle provides a structured framework for managing software projects from inception to completion and beyond. It outlines a series of distinct phases, each with its own objectives and deliverables, ensuring a systematic and organized approach to software development. The journey begins with requirements gathering, where the development team works closely with stakeholders to define the software's purpose, functionality, and constraints. This phase focuses on understanding user needs, business goals, and technical requirements, laying the foundation for a successful project. Once the requirements are clearly defined, the design phase takes center stage. Here, the software's architecture, data structures, and user interfaces take shape. Designers and developers collaborate to create blueprints and prototypes, ensuring that the proposed solution aligns with the gathered requirements. With a solid design in place, the implementation phase commences, where developers translate the design into tangible code. Programming languages, frameworks, and libraries become the tools of the trade as developers strive to write clean, efficient, and well-documented code. Testing, an integral part of the SDLC, ensures that the software behaves as expected and meets the defined quality standards. Different levels of testing, from unit testing individual components to system testing the integrated software, help identify and rectify defects before deployment. The deployment phase marks the culmination of the development efforts, where the software is released to its intended users. This phase involves installation, configuration, and data migration, ensuring a smooth transition for end users. The SDLC doesn't end with deployment. Maintenance is an ongoing phase that encompasses bug fixes, performance enhancements, and updates to accommodate evolving user needs and technological advancements. Over the years, various software development methodologies have emerged, each with its own philosophy, strengths, and weaknesses. Choosing the right methodology depends on project requirements, team structure, and organizational culture. The Waterfall model, a traditional approach, follows a linear and sequential process. Each phase of the SDLC is completed before moving on to the next, offering a structured approach suitable for projects with well-defined requirements and minimal anticipated changes. In contrast, Agile methodologies embrace iterative and incremental development, emphasizing flexibility and adaptability to changing requirements. Agile methodologies such as Scrum and Kanban prioritize collaboration, customer feedback, and continuous improvement throughout the development lifecycle. DevOps, a cultural and technical movement, promotes collaboration between development and operations teams, aiming to shorten development cycles, increase deployment frequency, and deliver software more rapidly and reliably. Lean software development, inspired by lean manufacturing principles, focuses on eliminating waste, maximizing efficiency, and delivering value to customers. It encourages continuous improvement and experimentation, striving to build only what is needed when it is needed. Extreme programming, an agile methodology, emphasizes customer satisfaction, teamwork, and continuous feedback. It advocates for practices like pair programming, test-driven development, and frequent releases, aiming for high-quality software delivered rapidly. Essential tools of the trade: technologies for software development. Software development relies on a vast array of technologies, from programming languages to cloud infrastructure, each playing a crucial role in bringing software to life. Programming languages, the building blocks of software, provide the syntax and semantics for instructing computers. Popular languages like Python, Java, JavaScript, C++, and C# offer different features and paradigms, catering to various development needs. Frameworks built on top of programming languages provide reusable components and libraries that simplify common development tasks. They offer a structured foundation for building applications, reducing boilerplate code, and accelerating development. Libraries, collections of pre-written code, provide ready-made solutions for specific functionalities. Leveraging libraries saves developers time and effort, allowing them to focus on higher-level logic rather than reinventing the wheel. Version control systems, such as Git, are essential for tracking changes to code, collaborating on projects, and managing different versions of software. They provide a safety net for developers, enabling them to revert to previous versions if needed. Cloud infrastructure, offering on-demand computing resources, has revolutionized software development and deployment. Cloud platforms like AWS, Azure, and Google Cloud provide scalable storage, databases, and servers, enabling developers to build and deploy applications without managing physical hardware. Overcoming common challenges in software development. Software development is not without its challenges. From ever-changing requirements to technical debt, developers must navigate a complex landscape while striving to deliver high-quality software. Changing requirements, a common occurrence in software projects, can derail timelines and introduce complexities. Embracing agile methodologies and maintaining open communication with stakeholders can help mitigate the impact of evolving requirements. Technical debt accrued from taking shortcuts or making suboptimal decisions during development can lead to maintenance nightmares and hinder future development. Addressing technical debt proactively through refactoring and code improvements is crucial for maintaining a healthy code base. Scalability, the ability of software to handle increasing workloads, is paramount for applications expected to grow over time. Designing software with scalability in mind, using appropriate architectures and technologies, ensures that the system can handle future demands. Performance, often a critical factor in user satisfaction, requires careful optimization of code, databases, and infrastructure. Monitoring performance, identifying bottlenecks, and implementing optimizations are essential for delivering a responsive and efficient user experience. Security, paramount in today's digital landscape, requires a proactive approach to identify and mitigate vulnerabilities. Security best practices, from secure coding to penetration testing, should be integrated throughout the SDLC to protect sensitive data and ensure system integrity. The importance of continuous learning in a dynamic field. The field of software development is in a constant state of flux, with new technologies, methodologies, and best practices emerging regularly. Continuous learning is not just an option, but a necessity for software developers to stay relevant and thrive in this dynamic environment. Staying abreast of industry trends, exploring new programming languages, and experimenting with emerging technologies are essential for professional growth. Online courses, industry conferences, and open-source contributions provide valuable avenues for continuous learning and skill development. The role of abstraction in managing complexity. Abstraction, often considered a cornerstone of software engineering, empowers developers to grapple with complexity by concealing unnecessary details and presenting only the essential information. Consider the analogy of a car. A driver doesn't need to understand the intricate workings of the engine, transmission, or electrical system to operate the vehicle effectively. Abstraction, in this case, is provided by the car's interface, the steering wheel, pedals, and dashboard, which hides the underlying complexities and allows the driver to interact with the car at a higher level. Similarly, in software development, abstraction allows developers to break down complex systems into more manageable layers, each with its own level of detail. By abstracting away the complexities of lower-level components, developers can focus on the higher-level logic and functionality of the system. For instance, consider a software library that provides functions for networking. The library's internal implementation, involving intricate details of network protocols and socket programming, can be hidden behind a simpler interface. This interface might consist of functions like connect, send, and receive, allowing developers to utilize the library's networking capabilities without needing to delve into the complexities of network programming. Abstraction, therefore, plays a crucial role in managing complexity by simplifying development. By hiding unnecessary details, abstraction allows developers to focus on the essential aspects of the system, making the development process more efficient and less error-prone. Enhancing maintainability. Changes made to the internal implementation of an abstracted component are less likely to impact other parts of the system, making the software easier to maintain and update. Promoting reusability. Well-abstracted components can be easily reused in different parts of the system, or even in different projects, saving development time and effort. Modularity and encapsulation, building reusable and maintainable software. Modularity and encapsulation, two closely related principles, go hand in hand with abstraction to further enhance the organization, maintainability, and reusability of software systems. Modularity encourages the decomposition of complex systems into smaller, more manageable modules, each responsible for a specific functionality. These modules act like building blocks, allowing developers to assemble complex systems by combining and connecting these independent units. Think of a house built room by room. Each room serves a distinct purpose: the kitchen for cooking, the bedroom for sleeping, the bathroom for hygiene, and is designed and constructed as a separate unit. Similarly, in software development, modularity promotes the creation of self-contained units of code, each with a well-defined responsibility. This approach offers several advantages. Improved organization. Breaking down a large system into smaller modules makes the code base more organized and easier to navigate. Enhanced maintainability. Changes made to one module are less likely to affect other modules, making it easier to maintain and update the system. Increased reusability. Well-designed modules can be reused in different parts of the system or even in different projects, saving development time and effort. Encapsulation, closely tied to modularity, emphasizes hiding the internal workings of a module and exposing only a well-defined interface for interaction. This principle, often referred to as information hiding, protects the module's internal data and logic from unintended external access. Imagine a car engine. The engine's internal workings, the pistons, cylinders, spark plugs, are hidden from the driver behind a protective casing. The driver interacts with the engine through a well-defined interface, the accelerator, gear shift, and ignition without needing to understand the intricacies of the engine's internal mechanisms. Similarly, in software development, encapsulation ensures that the internal details of a module are hidden from other parts of the system. This approach offers several benefits. Reduced complexity. By hiding internal details, encapsulation simplifies the interaction between modules, making the system easier to understand and maintain. Increased flexibility. Changes to the internal implementation of a module can be made without affecting other parts of the system, as long as the module's interface remains consistent. Enhanced security encapsulation helps protect the integrity of a module's data and logic by preventing unauthorized access or modification. Separation of concerns, achieving clarity and flexibility in design. Separation of concerns, a fundamental principle in software engineering, advocates for dividing a computer program into distinct sections, each addressing a specific concern. A concern in this context represents a particular aspect or functionality of the software system. Imagine designing a house instead of trying to cram all functionalities, cooking, sleeping, bathing, into a single chaotic space. We separate these concerns into distinct rooms: the kitchen for cooking, the bedroom for sleeping, the bathroom for bathing. This separation allows for specialization and clarity, making the house more organized, functional, and easier to maintain. Each room can be designed and furnished independently, catering to its specific purpose without interfering with the functionality of other rooms. Similarly, in software development, separation of concerns encourages the decomposition of a complex system into distinct modules or layers, each responsible for a specific concern. For instance, a web application might be separated into the following layers. Presentation layer, responsible for handling user interface and user interactions. Business logic layer contains the application's core logic, rules, and workflows. Data access layer handles data persistence, retrieval, and manipulation. By separating these concerns into distinct layers, we achieve several benefits. Improved modularity. Each layer can be developed, tested, and maintained independently, promoting modularity and reusability. Increased flexibility. Changes made to one layer are less likely to impact other layers, making the system more adaptable to future modifications. Enhanced testability. Separating concerns facilitates unit testing, as each layer can be tested in isolation, ensuring the correctness of individual components. Separation of concerns fosters a more organized, maintainable, and flexible software architecture, leading to higher quality software that is easier to understand, modify, and extend over time. Conclusion. Embracing the ever-evolving world of software development. The realm of software development is a dynamic and ever-evolving landscape demanding adaptability, continuous learning, and a deep understanding of fundamental principles. By embracing core principles like abstraction, modularity, encapsulation, and separation of concerns, developers can build robust, maintainable, and scalable software systems. The software development lifecycle, with its structured phases, provides a roadmap for navigating the development process, while various methodologies from Waterfall to Agile offer flexible approaches tailored to different project needs. As technology advances and user expectations evolve, software developers must embrace continuous learning, exploring new tools, languages, and methodologies to stay at the forefront of innovation. The journey of software development is one of continuous growth, adaptation, and the pursuit of crafting elegant and effective solutions to real-world challenges.